Welcome back to the deep dive. So, if you're working in security operations today, you're probably completely buried under logs, right? Just this astronomical amount of data.
Oh, absolutely. Some security information and event management systems, they're essential, no doubt.
Yeah.
But just having one, well, it doesn't really cut it.
Exactly. You've got to know how to actually use it, how to sift through all that noise and, spot the critical thing before something bad happens.
That's really the core of it. We're not diving into abstract security ideas today. This is about the actual practical mechanics. We've essentially distilled the key techniques professionals use, drawing from training for platforms like, say, FortiSIEM 7.2.
Yeah, this isn't just abstract theory. This is the stuff that, makes the difference between someone just running a SIEM and someone truly mastering it.
Our goal here is really to pull out the nuts and bolts. How do analysts query these huge data sets effectively? How do they add context, set up smart detection rules, and crucially take immediate action when a threat pops up?
Okay, let's unpack this. First off, that sheer volume problem, you mentioned it, billions of events maybe? How does an analyst even begin to look for one specific suspicious thing?
It really starts with understanding the query language,
Right.
specifically the logical operators. Let's say an analyst is looking for something specific. They suspect an attack from a known bad IP address.
Right, okay.
And they only want to see events from that IP if they're also marked as high severity.
Ah, so it has to be both things at once, not just one or the other.
Precisely. If they use the OR operator instead, they get every single event from that bad IP, plus every single high-severity event from anywhere else on the network. It's just
a massive data dump.
Yeah.
Useless.
Totally useless. So the operator you need when you require both conditions, the specific IP and the high severity, is A&D.
Right. And D for needing both. Makes sense.
It's absolutely essential for that kind of precision. And it's not just about making the results manageable for the analyst. It ties into how these systems perform at scale.
Oh, interesting. How does using A&D affect performance, especially in bigger environments?
Well, think about cloud environments, the kind of thing the source material calls cloud scalability. If you run a really broad, inefficient query, like using OR improperly across a large distributed system.
You'd bog things down.
Exactly. You could strain resources, slow down analysis for everyone. Using A&D to be precise isn't just nice. It's basically a requirement for efficiency when you're dealing with huge amounts of data.
Okay, efficiency scales, inefficiency just gets worse. Got it. So let's say they use A&D. They narrow it down. But often, they don't want just the raw logs, right? They need a summary. Like, how many login failures per user in the last day? How do you get that summary view?
Right. You're moving into aggregation now. To get a total count of something, like all login failures that match your criteria, you use the count-IH aggregation method. Simple enough. It just counts the records.
But wait, if I just run count on login failures, I get one big number, right? Like 5,000 failures. That doesn't tell me who failed. Was it one person trying 5,000 times, or?
Exactly. That's where structure comes in. A raw count isn't always enough. To make that count meaningful, to see the count per user, or say by source IP, you need to combine count with the groupie by clause.
Ah, okay. So groupie by Y tells the system, count everything, but then split those counts into separate buckets based on this field, like username or source IP.
Precisely. So instead of just 5,000 failures, you see user A, 50 failures, user B, 10 failures, and maybe source IP 1.2.2.4, 4,900 failures.
And that tells a story. Suddenly you see the brute force attack standing out.
That's the power. It turns raw numbers into actual intelligence, identifying patterns, finding those top talkers. Group PY is fundamental for that.
Okay, here's where it gets really interesting. We're moving past just finding and counting things. We're talking about making the data smarter, more predictive. Because a raw log, IP, time, severity, it often isn't enough to be really sure about a response, is it?
No, it's often too sterile. It lacks context. And that's exactly why analysts need lookup tables, their primary job, to enrich event data.
Enrich, what does that actually look like in practice?
Okay, imagine a log event just says user ID 4051 access to file. The log itself doesn't know who that is, but maybe you have an external HR database.
Right.
And that database maps user ID 4051 to, say, Jane Smith, Finance Department, New York office. You configure the SIEM to use this database as a lookup table.
So when that event comes in,
The SIEM automatically looks up 4051 and adds Jane Smith, Finance, New York, right into the event details.
Wow. Okay. So a basic firewall log suddenly tells you who and where. That completely changes how you might triage it, right? An event from a regular user might be low priority, but the same event from an executive ID, that gets looked at immediately.
Exactly. The lookup table injects that crucial context that the original device just didn't have. It's vital for accurate assessment.
That handles context that's kind of static, like user roles. But what about threats that aren't just one single event? Like attackers often work in stages, right? Reconnaissance, then maybe login attempts, a sequence of actions.
Yeah, you need rules that track state over time, not just single isolated events. Think about a brute force or dictionary attack. Maybe hundreds of failed logins from one IP in just a few minutes.
You can't just trigger an alert on every failed login. That'd be way too noisy.
Right. So you need a way to define that specific pattern. Multiple failures, same source, short time frame. That's where the sub-pattern component in an analytics rule comes in.
A sub-pattern. Okay.
It's designed specifically to define those recurring or sequential conditions. It lets you specify the exact chain of events, maybe event A followed by event B, or event C happening 5 times in 60 seconds from the same source that has to occur before an incident is triggered.
Can you give an example of how that might go wrong if you don't use a sub-pattern correctly?
Sure. Let's say you just write a rule. Alert if 3 failed logins occur. Simple, right?
Seems simple.
But without a sub-pattern requiring those 3 failures to be from the same source IP within, say, 1 minute, that rule is practically useless. It'll trigger constantly just from normal user typos across the company.
Ah, I see. 3 different people in different cities mistype their passwords around the same time and bang, false alarm.
Exactly. The sub-pattern enforces that critical context, temporal proximity, source consistency that distinguishes a real targeted attack pattern from random noise. What's fascinating here is how we connect that kind of precise detection to more automated intelligence and faster response. The modern SIEM is definitely moving beyond just relying on analysts manually writing every single rule.
Which brings us nicely to machine learning ML. How does that change the game for the security analyst?
Well, the really key benefit of using ML tasks in a SIEM is that they can automatically figure out what's normal. They establish a baseline of normal behavior for your specific network, your users, your servers.
Humans can't possibly define normal for everything, everywhere, all the time. It's too complex.
Exactly. The ML system learns it. It learns what Tuesday at 2 p.m. usually looks like on your network.
And once it knows normal, anything abnormal stands out.
Precisely. It allows the system to proactively flag anomalies behavior that's weird or suspicious because it deviates from that learned baseline, even if it doesn't technically break a predefined security rule.
Like, maybe a user suddenly accessing a database they've literally never touched before, or logging in from a completely new country.
Those are perfect examples, things that a static rule might miss, but that deviate significantly from the established pattern.
Now, the source material connects this idea of automated, resilient detection to the concept of high availability. How do those relate?
Well, think about it. If your detection relies solely on manually written rules, what happens if those rules have errors, or they become outdated because the threat landscape changed? Your detection capability might effectively become unavailable, or at least severely degraded.
Right.
ML-based baselining provides this sort of continuous adaptive detection layer that doesn't need constant manual tuning just to stay functional. It offers a more resilient, highly available form of detection, essential when things change so fast.
Okay, makes sense. So the system detects something, maybe a high-severity anomaly via ML. The analyst needs to know immediately. Seems obvious, but what's the actual configuration piece needed to make sure, say, an email alert goes out?
Ah, yes. That alert doesn't just happen automatically. To get that email notification for a high-severity incident, you absolutely must configure it within the notification policies.
Notification policies, okay.
These policies are the control center. They define how alerts get sent, who they go to, and under what conditions. It's that critical bridge between the system spotting something and a human actually finding out about it. You have to set it up.
And talking about human response, the absolute key in incident response is speed, right? Minimizing that dwell time. If an analyst confirms, yep, this machine is compromised, they can't wait around for someone else to maybe update a firewall rule hours later.
No way.
Yeah.
That's where the remediation function becomes so valuable. Think of remediation actions as the analyst's immediate response toolkit right there in the SIEM interface.
So they can act instantly.
Yes. They can trigger predefined actions directly from the incident screen. No need to log into another system, no need to open a ticket and wait.
What kind of actions are we talking about typically?
Common ones are things like isolating the compromised host from the rest of the network, or blocking the malicious source IP address at the firewall, maybe even running a pre-approved script on the machine to start cleanup.
Instant containment.
That's the goal, cutting that time from detection to containment down from minutes or hours to literally seconds. That can make a huge difference in stopping ransomware spread or data theft.
So what does this all mean? We've gone through specific SIEM tools, querying, enriching data, detecting patterns, taking action. How does all this internal SIEM capability fit into the bigger picture of modern security, like Zero Trust Network Access, ZTNA?
Right, ZTNA is really the direction things are heading. The core idea is never trust, always verify, continuously check everything, users, devices based on context, not just network location.
And the SIEM, with all this data and analysis, it's like the ultimate context engine.
Exactly. The integration between a powerful SIEM and ZTNA is critical. FortiSIEM, for example, uses its user and entity behavior analytics (UEBA) capabilities to feed dynamic context into the ZTNA system.
UBA, that's related to the ML baselining we talked about, understanding normal behavior.
Yes. UEBA analyzes those behavior patterns, spots deviations, and calculates a real-time risk score for users and devices.
And crucially, that risk score isn't just stuck inside the SIEM.
Nope. It gets fed directly to the ZTNA policy engine. So if the SIEM's UEBA sees weird activity, maybe that user accessing strange databases, it bumps up their risk score.
And ZTNA uses that score.
Instantly. The ZTNA system uses that dynamic risk context from the SIEM to enforce policy.
So instead of a simple rule like user X can access server Y, the rule becomes something like user X can access server Y unless their real-time risk score from the SIEM goes above 70, then block them immediately.
That's the core implication. Dynamic, context-aware policy enforcement. It's absolutely vital today, especially in flexible environments like infrastructure as a service, where users and systems are constantly changing. Static boundaries don't work anymore. You need that continuous behavioral verification. Back to broader business concepts like solution selection based on business growth. We touched on how SIEMs need scalability and high availability to support growth. But thinking strategically, if a SIEM's value is tied to business growth, what critical analytical capability, maybe beyond just detecting today's threats, does it need to truly align with the company's long-term strategic goals and risk management?
That's a great question to leave folks with. Something more than just detection. What's the next level of strategic value? Interesting thought.